Hi, everyone, and welcome to lesson 24. This lesson will learn about the first law of thermodynamics. We'll learn what this law is, and then we'll also learn how to apply it to some thermal processing. All right, so if you recall back from when we studied work and energy in the previous course, remember that the total energy of a system is the sum of the mechanical and thermal energy. So we mostly focus on the mechanical energy, the potential energy, the kinetic energy. We talked a little bit about thermal energy and how the friction will lead to thermal energy and heat, but for the most part, we ignored that part. So now, since we're learning about heat and thermodynamics, now we really want to get into that part, the thermal energy part. So if remember when we also talked about systems and environments, okay, where we specifically defined a system as being a certain group of objects or something, and then we have an environment, everything else outside the environment. And then we said, well, we can isolate a system so that everything in the environment doesn't affect what's inside the system. So if we do this, if we isolate a system, then the external work from the environment is zero. And that's nice. So if we can do this, if we can define a system and isolate it, then the total energy of the system will remain the same. So we know that's not how real life works, but that's part of physics, is we're trying to simplify things so we can actually tackle it in a possible and make it possible to tackle. So the mechanical energy, that potential energy, kinetic energy, we can also refer to that as macroscopic energy. Okay, macroscopic. Okay, large things that we can see. And we can refer to thermal energy as microscopic energy. Okay, and so we can't see it, but it's happening, and it's happening because the atoms and molecules are in motion, right? And depending on how much motion, how fast they're moving, there can be a lot of thermal energy or less thermal energy. Okay, so we can have an isolated system, but we can also have a system where external work is applied to the system. So we have an environment, we're not completely isolating it, so we can actually apply work to the system. And what this will do is cause the system's energy to change. And so when the thermal energy changes, when we have work that causes a thermal energy change, we call this heat. Okay, so heat is essentially a change in thermal energy, and we symbolize it with a capital Q. Okay, and so then this total energy equation we can then write as it's the total is the mechanical energy, right, plus the thermal. I guess I don't need to rewrite that. But it's also equal to the work done, right? If we have work being done on the system, and the energy, the thermal energy that's been changed or transferred, that heat. Okay, so the units of heat, since it's a type of energy, is still a joule. Okay, you'll remember that from the previous course, a joule. there's a couple other terms. So um, when this part of thermodynamics was still being worked out and figured out, it was referred to one of the units was called a calorie. Okay, so we're familiar with that. That calorie still exists, and it's equivalent to 4.186 joules. Okay. And so we've heard of calorie before, but a calorie, technically, the calorie that you see, like a food calorie, is called the kilocalorie. Okay, so if you look at nutrition labels, they will usually say kcal or something like that. That's what. So if you read the label on something, and water doesn't have it, but combos here, it tells me I have 240 calories. Okay, and so those are the kilocalories. Okay. So that's what that means. And so the SI units of energy, of heat energy, since it's a type of energy, is still going to be the joule. Okay. And interestingly, the calorie was defined, we still define it as how much heat is needed to change the temperature of 1 gram of water by 1 degree Celsius. Okay. And so the kilocalorie would be 1 kilogram of water by 1 degree Celsius. So heat is energy. It's energy that's transferred between the system and the environment. And the way it works is that the energy is transferred when these faster moving molecules interact with cooler or slower moving molecules. So the hotter molecules will have faster movement. They're moving faster. Okay? And the cooler molecules or the cooler object, they're still moving, but not as fast. They're moving slower. Okay? And one thing we'll see here, we'll see in a couple more lessons, especially how important this is. It actually comes down to the second law of thermodynamics, but it's that this heat energy is always transferred from the hotter object to the colder object. Right? Heat is a one-way street. It only goes from the hot to the cold. Okay? There's really no such thing as cold. There's the absence of heat. There's heat and the absence of heat, or less heat. So that's the direction. So that's important. And they will always do this until they reach a thermal equilibrium. So if you take coffee and you put cream in your coffee, the cream came out of the refrigerator and you're having hot coffee, then it will all come to an equilibrium where the cream coffee mix is now at one temperature. All right, so we looked at this idea of a piston. Okay, so remember I showed you my syringe, right? So this idea of the cylinder with a piston inside. If we have this rigid cylinder, like we have here, and then we have a piston inside that's free to move up and down. What we see is that we could say that the system is the gas that's inside, right? If we have trapped gas inside. And so if the piston moves, then work is being done on the gas, okay, by the environment. Okay, that's important. Okay, so we could say work is done by the environment. want to point that out because you may want to think of the work being done as being done by the piston itself. Okay, so the piston has mass, it has weights, but it's the atmosphere, right? The atmospheric pressure that is going to do work, right? That's the external environment. Okay, so the environment is doing the work, not the piston itself. Okay, and so what about? Remember, we talked about work in the previous course, and work can be done. It's a vector quantity, so it can be done in one direction or another. And so the way to think of this is to sort of put the cylinder on an XY axis. Okay, X, Y, and so what happens is, say the gas expands. That means that the gas will exert an upward force on the piston. Okay, it expands, it exerts an upward force on the piston, pushing it upward. But the environment exerts a downward force on the gas. Okay, it uses the piston to do that, but the environment is what exerts a force back downward. Okay, so we have sort of like Newton's third law, right? We have action-reaction pair. And so what we see is by thinking of the X and Y axis in this way, is that if the piston moves up, okay, and the work from the environment points down, it's pointing in the negative direction. Okay, so the work we would say is negative, right, if the gas is expanding. Okay, and so if we look on a pressure volume graph like we introduced in the previous lesson, and let's say we have a constant pressure. Let's look at constant pressure, which is what we would have if we had a cylinder with a piston, right? Atmospheric pressure is constant, we learned, and so it would be in a constant pressure. And so if it expanded, we could say that it had an initial volume, right, and then a final volume. Okay. And then we could draw a little diagram showing how it went from a smaller volume to a larger volume. It expanded. Okay. And so the work, what we could see here is that the work done is that area under the curve, okay, or more specifically, the negative of the area under the curve, right? So it's a pressure versus change in volume. Okay, so we say negative because it's going in the opposite direction of the gas expanding. Okay, if the gas were to compress instead, the work would be positive. Okay, and if you do the math out, you'll see that if we do V final minus V initial, if it was the other way around, then we would have a negative number if it was compressing going the other way. And those two negatives would cancel, and we would have positive work for the compression. Okay, so maybe we can have a little note here that the gas expands. Okay, then the work done on the gas is negative. Okay, if it compresses, then the work done is positive. So the constant pressure process um, is what we have here when we just have this, when the only pressure happening is from the atmosphere. Um, and and this and it's coming from the atmosphere and the weight of the piston, right? The atmosphere is using the piston, um, and so we can use the weight of the piston to determine the pressure. Okay, and of course we see, like we saw before, then on the pressure volume graph, this is just a flat line. So the area under the curve is pretty simple. It's just pressure times change in volume. Okay. So what about a constant volume process? Remember we said we would have the volume was constant, then maybe the pressure changed, so it's going to look like a vertical line. And so if the work is the negative of the area under the curve, well, that tells us what? That in a constant volume process, no work is done. Okay, so we're going to see a few more processes that happen here and what happens with each and how that relates to the thermal energy and the work done in the heats. But before we move on to that, let's just try a couple examples here of a piston, right? Dealing with a piston, and looking at trying to do some practice with the work done by the environment on the piston. So let's say we have a 2 centimeter thick movable vibranium piston. Some of you know what vibranium is. And it floats on air and a cylinder. So we have a cylinder with air, and the piston is made of this, this sort of made up vibranium. And so what is the pressure on the air in the cylinder? Okay, so pressure, right, is force per area. We're not given the mass, but we are given how thick. How thick is this vibranium? So if it's in a cylinder, then we sort of have a disk, right? A disk of mass here. So we don't know the mass, but so otherwise we could have said mass times gravity per area. But we do know we can find mass. Mass is related to density and volume. So it's density times volume times gravity over area. And if you look up, you can actually look up the density of vibranium, which I did, which is 0.497 grams per cubic centimeter. I don't know who determined that, but that's what I found online. So that's what we'll use. So then we can look at the now we know that the pressure, or we're looking for the pressure. We know the density, we know the volume, the area, gravity. So then we can actually calculate the pressure now. Okay, so the density is 0.497, and we're going to want to convert that first, right? So just as a side, remember we want that into SI units of kilograms per cubic meter, not grams per cubic centimeter. Okay, and so we had a little conversion factor I shared with you in the previous lesson and the one before that. Um, First, if we go from grams to kilograms, well, remember we said that the conversion factor of 1 cubic centimeter was 10 to the minus 6 cubic meters. Okay? And so then I get 49.7 kilograms per cubic meter. Okay, and then volume, all right, so volume is going to be the area, area times the height. So the area is pi, and I see here that it's 5 centimeter diameter, so it's going to be 2.5 centimeters or 0.025 meters radius pi r squared. Right, so area, so volume is the area times the height. Okay, so the height, since we're trying to figure out the pressure coming from the external environment, right, which is using the piston, then, then we're going to want to know what's the height or the thickness of the cylinder. So that's going to be 0.02 meters. All right, and then times gravity. All right, over the area, okay, which is also pi r squared. So what we see here is that our areas essentially cancel. Okay, and let's see, what do we got here? So 7. Okay, and I get a pressure of 9.7. And so we're in SI units, so that's going to be in pascals. Okay, it's kind of a tiny amount of pressure there. But vibranium has some interesting characteristics too. So if we were to do this with something else, we'd probably see a lot more pressure. So the vibranium is very light. If we were to use like a more typical metal, we'll probably see a larger pressure being exerted. Okay, so we found the pressure on the air due to the environment, which uses the piston to exert work on the air. All right, so about how many air molecules are in the cylinder if the temperature is 35 degrees Celsius? And so if we want to know how many molecules there are, we would want to use the ideal gas law in the form of N, right? nRT form, because N is our number of moles. Then we can easily transfer that to number of molecules. So N is V over RT. So we got the pressure to be 9.7 pascals. And so the volume is the area times the height. So pi r squared times the height. Now this time, in the previous one we used the height, the thickness of the cylinder, because we're trying to figure out what the pressure is being exerted by the environment through the cylinder. And now we want to know how many air molecules are actually inside the container. How many are in the air there? So now the height we're going to use is the height of how high the piston is up, right? The height of the air. So that would be 0.1 meters. R is our universal gas constant, 8.31 joules per mole Kelvin. And temperature. So we're given 35 degrees Celsius, but we're going to want to put this into Kelvin because Kelvin's the SI unit and we're not comparing anything. So we want to know an actual amount. So we have to use Kelvins here. Okay. So I get, if I did it right, 7.4 times 10 to the minus 7th moles. Okay, so, but we want to know how many air molecules are there. So, number of air molecules is number of moles times Avogadro's number. Okay, so I get 4.5 times 10 to the 17th molecules of air. Okay. Now, how about if the temperature increases by 20 degrees Celsius, how much will the piston move? Okay. So now we can apply. We can think here. Remember, we have a constant pressure process. And we can apply what we learned before that if we have if we have if we have we're going to keep we're not changing the amount of air, okay? So then PV over T equals NR is constant, okay? So we're not changing the amount of air, the amount of molecules, so that's constant. So that means that whatever our final pressure, final volume, and final temperature are, have to be the same as our initial pressure, volume, and temperature ratio, right? And it's a constant pressure process, so we can forget about those pressures will cancel out. But we want to know how much will the piston move. So essentially, how high up will it go if we increase? If we increase the temperature, the volume will increase. The piston will rise to certain heights. Okay. So volume, remember, is we rewrite this. Volume is area times height, right? And we could say the area is the same, but there'll be a final height and an initial height. Okay, so if we solve for final heights, And we also see that our areas, our areas will cancel. Okay, so it's just the initial heights, the 0.1 meters. The initial temperature, or sorry, the final temperature, which is going to be, what that, 35 plus 273 to get the Kelvin. Now we're adding 20 over the initial temperature of just the 35 plus 273. And I got 0.106 meters. Okay. So that's the new height of the piston. Okay. That's not what the question asked for, though. It said, how much will the piston move? Okay. So it was initially at 0.1 meter, right? So this is really just the change in height. It went from 0.1 meter to 0.106 meters, right? This is not the change in height. So the change in height is actually going to be 0.006 meters. That's what the question's asking. Okay. Hopefully you're still following along, but this is a lot, I know, but this is also some pretty high-end tough work we're doing here. So if you follow this, it'll really help you through one of the tougher questions on the homework. All right, so how about work? How much work is done on the air as the piston rises? Okay, so notice how it's also describing in detail that how much work is done on the air as the piston rises, right? So the piston, right? Piston moves up, right? But the work from the environment is down, right? All right, so work, we said, was minus pressure times change in volume. All right, the pressure was 9.7 pascals. Okay, and then the change in volume. Okay, so volume is area times height, so pi r squared is our area. Now our height, okay, it's how much work is done on the air as the piston rises. Okay? So that's where we're going to use our change in height from the previous question. That's what we want for our height. Because we're looking at the work done while the piston rises. Okay, and you get minus 1.14 times 10 to the minus 4. Okay. I remember also work, like energy, is in joules. Okay, and so we see by the negative sign, the work is downward, right? Okay. So what actually is this first law of thermodynamics? Um, so if we think about when when energy was transferred through mechanical means, right, we converted mechanical or potential energy to kinetic energy and back and forth. Those were dealing with macroscopic interactions. But heat, since we're dealing with the atoms and molecules, it only requires us to think about microscopic interactions. And we don't have to worry about those large macroscopic interactions. So if we just look at those microscopic interactions, then we can simplify the conservation of energy statement and equation to just be that if we're just dealing with the microscopic interactions, the thermal energy, all we're worrying about is the work done and the heat that's transferred. Okay, and so this is essentially by stating this way uh, that this is essentially the first law of thermodynamics. Okay, so it's not entirely huge that you memorize that or know how to state that, but that's essentially what the first law means. Okay, that we're just basically applying conservation of energy to these microscopic interactions. Okay. Now, there's three ideal gas processes that are important when we're dealing with these microscopic interactions. So the first one here, the isothermal process, where we have a constant temperature. Okay. So the temperature doesn't change, and so what that means is that the thermal energy doesn't change. Okay, and so if we consider our equation here, if that doesn't change, then all the energy that goes into a system as heat, okay, if heat's the only energy, then it has to be converted into work. Okay, so if we get rid of heat thermal, then we're just left with that the heat turns into the work, or the negative of the work, right, because it's going the other way. So for an isothermal process, for one where we have constant temperature, this is essentially the first law of thermodynamics, right? So heat turns into work turns into heat. Okay. Then there's the isochoric, or just the constant volume process, where we saw that with a constant volume process, since, go back to that slide quick. Right, so the constant volume process, where work is the area under the curve, well, there is no work done in a constant volume process. Right? There's no motion, there's no movement, change in volume, so there's no work done. Okay, and so then basically what this says is that the first law of thermodynamics says is that if there's no work done, then the change in thermal energy is completely due to the heat that's transferred. Okay, and then the other one, the adiabatic process, where there's constant heat or no heat is transferred, then basically the first law says that the thermal energy, right, is just comes from the amount of work done. Okay. All right. So that's essentially it for this lesson. We're going to keep going, moving on. We're going to look more at these processes and apply them, but it's just a good stopping point where I'd like you to hopefully focus on the few questions. I think that will help you to move on before going to the next lesson. So there are just a couple things I think will help you bring all this part together. And then notice that this one question here, 1949, there's one part, I think it's the C part, there's 5 parts. So you should be able to do all the parts now except for, I think, one of them, which I believe is the C part. So that's why the star. But so go ahead and give those a try. It's homework 11 now. And so did you learn how to apply the first law of thermodynamics to thermal processes? So in particular, we saw, we spent a lot of time with the isobaric process, the constant pressure process, where we saw that the work done is the negative of the area under the pressure volume graph. So whatever that pressure is, that constant pressure, the change in volume is due to the work that's done, okay, by the environment. Okay. Then we practiced that. We kind of brought it all together with what we learned from the previous lesson. So it was kind of complex, but that was most of what we learned. And then we started seeing what does this first law of thermodynamics actually mean, that we're just dealing with microscopic interactions. And since there's 3 parts of that first law, then there's 3 processes that we can have. Okay? And we'll get more into depth in that in the next lesson. But for now, that's it for lesson 24.